Perfect. Okay, now we're recording. All right. So, the middle of the book here, uh, it calls this systems, where it talks about data storage, tree indexes, hash indexes. This text holds off until kind of the middle of the book. I prefer starting there because, in my opinion, it's good to um, have that kind of background knowledge before we get into theory and before we get into practice, like what's happening behind the scenes. I like covering those things in the beginning. Now we're going to be getting into ER diagrams and relational algebra. And according to this textbook, that's like chapter 2, chapter 3 stuff. So if you want to read ahead or anything, you can feel free to start reading those chapters now. Especially chapter 2 deals with ER diagrams. By next week, we'll be moving into chapter 3 on the relational algebra, relational calculus, which are fancy sounding words for things that actually aren't so bad. And this theory section that we're in right now, the reason why we're going through it is before you start learning the grammar with SQL and making SQL queries, we're going to learn about set theory. So when you have a huge amount of data, you throw it inside of a database, and the data inside of the database can be thought about as a set, with each record being an element of the set. And in fact, it's not just going to be in sort of one location, but it will turn out that you take your gigantic amount of data and you start splitting it up into tables. So this part of the data, I'm going to throw that in this table. This part of the data, I'm going to throw it in another table, and then another table. And now I'm just going to have a huge collection of tables. And these tables will kind of connect with one another. And how to think about all of that is the point of the next couple of weeks. Particularly, seemingly simple queries, which is when you want to you have a bunch of data that's in the database and you want to put together some type of query to be returned some number of records. How do you phrase the query? In English, some of these are pretty simple sounding, but the query that you need to write in the SQL language can look complicated. And so this is the point of going through this theory part, to appreciate how to interpret a question in English and to be able to formulate that as a query in general and then specifically in SQL. Hopefully after this whole theory thing, the application part will just sort of fall out and it won't be that big of a jump. But learning relational algebra will allow you to make proper queries, even difficult ones in SQL. So that's the next couple of weeks. I'm again still trying to. I think we're still on pace to cover theory and then to get into practice and end this semester with you having like hands-on experience with an actual database in the real world, doing stuff on the cloud, and all of that. We're in like mid-October now. We still have time for all of that. Okay. So that's where we're going. And let me start talking about ER diagrams. Again, this will be sort of a blip with our with the next few weeks talking about theory. There's not a lot to say about ER diagrams, but it's important to go through it sort of carefully. It will take maybe this class and the next class, and then we'll move on. Okay, so an ER diagram, an entity relationship diagram, is a diagram that you draw. So it's a diagram, it's going to be a picture. And the point of this picture, I want to emphasize in the beginning, this isn't a doodle where you have an idea in your mind and you're just going to be drawing some stuff here and there to try to express to other people the sort of idea that you have in your head. It is not that. It is a picture, but the reason for the picture, there's rules. And certain pictures are right, other pictures are wrong. And the reason for it is to be able to figure out how to construct tables given data. So you have a bunch of data. These are going to be translated into a series of different tables. And this process of drawing a diagram is to help be a medium step between how exactly should I make my tables look so that it matches the requirements of whoever has the data and wants to interact with it. So first I'm going to turn off the video and start off with what, I don't know, I will call the vocabulary of ER diagrams. So this is vocabulary. And we're talking about diagrams, which are pictures. So an ER diagram is an entity relationship diagram. Entities are going to be rectangles. Relationships are going to be diamonds. Oh, sorry. Another quick aside before I get too deep into this. If you Google ER diagrams, entity relationship diagrams, you will see very likely different symbols than the ones that I'm teaching in this class. This book, again, 2003. I'm sticking to the standard that this book uses. Okay, ER diagrams. There's other ways of drawing things that are all conveying the same idea. I think once you understand them, it's not too big of a jump to take your pictures and be able to translate them into somebody else's pictures where maybe each of you learn the same thing just from different texts and stuff like this. So don't be confused if you look online for resources on ER diagrams and what they are. I'm sticking to the standard in this book because, well, for a course, I think it's good to have a text and to stick to it. So, okay, that's my aside. All right, so we have entities, relationships. Entities cannot directly connect to other entities. Not allowed. The only way that entities can connect with each other is via a relationship. Okay, so if you have some entity A and some entity B, there you cannot directly connect to them or connect these two entities. Entities, in all cases, are connected via some relationship. Okay, so that's good. That's not good. All right. So we have entities, relationships, attributes are going to be ovals. Keyed attributes are ovals with text that's underlined. And then the edges. So these are all of the blobs, I guess, that will appear in ER diagrams. Now, attributes. Let me get rid of this here. Okay. A, B, R. So here are two entities, entity A, entity B. They're connected via a relationship R. Attributes, both entities and relationships can have their own attributes. So this is the way that the diagram is kind of going to look. There's going to be ovals that stick out from rectangles or diamonds. For entities, some of these will be keyed attributes. So in this case, A has two attributes. One of them is a keyed attribute. That's the little a. B has its own keyed attribute, D. And then there's other attributes. Fine. Now you'll notice that I'm also drawing lines connecting these. And this is the only other part to the vocabulary. We will have connections. This is called, these are unconstrained. These are thin lines. So right now in this diagram here, everything is unconstrained. The constraints, by the way, will be happening here on where the entities connect to the relationship. That is where these lines are. All the other lines are thin lines, and they don't really mean anything. But for the lines that connect entities to relationships, we have a few different flavors. One is, as there is now, thin lines. These mean that the entities have an unconstrained relationship or are unconstrained in their relationship. We will have thin arrows, and this means at most one. We will have thick lines. These will correspond to at least one. And then if you have at most one and at least one, so there's at least one and if we add an arrow to it, then that's also at most 1. And if you combine both of those, that results in being exactly 1. Okay, and that's it. These types of connections are called participation constraints. Okay, and these participation constraints, again, are only here where the entities connect with a relationship. So what is this? At most 1, at least 1, exactly 1, blah. Let me give a slightly more concrete example. Let's say we have employees and departments. So these are 2 entities. And employees, this concept, has certain attributes. Let's call it a social security number, a name of the employee, and a parking lot that they park in. Departments can have a department ID. They can have a name. I'll say D name. So that's a department name and a budget. Okay? So employees and departments, these are 2 kind of abstract ideas. Employees will be identified by the combination of their social security name, the name, and the lot. Departments will be identified by their department ID, the department name, and the budget that the department has. How are employees and departments related? Again, we cannot just do this. We can't connect them. They need to go through a relationship. I'll call this relationship works in. Okay, employees work in a department. And for this relationship, employees can work in a department since some time. All right? Now, for the keyed attributes, I'm going to choose for the employee the social security number, and for the department ID, or the department ID for the departments. Okay, so a keyed attribute just means that you're going to be using this attribute as a key. The key here is the thing of which you'll be constructing your index table, right? So when we talked about B+ trees or hash tables, well, for example, like for a B+ tree, you had to have some attribute or some key that has a natural ordering to it, such that you can construct the key or construct the tree based on it, right? So some things appear before others, and now you can break left, break right, or there's a way to traverse the tree based on this key. So here, employees would be keyed by their social security number. So based on the social security number, you could have a B+ tree, for example. And the B+ tree, the key is the social security number alone. And then once you go through the B+ tree and you find a record, that record will return social security number, name, and lot. That whole row. Okay, so that's a keyed attribute. Let me turn this off again. I want to say ahead of time that the entities here, this will be translated to a table. The table will have a name, and that's the name of the entity. Okay, so there's going to be some table. Like first you draw the diagram just to figure out what the attributes, what the characteristics are of the data that you're working with. But at the end of the day, entities are going to be translated into a table, and tables will have different columns. In this case, this table will have a social security number, a name, and a lot. Similarly, this department entity will result in its own table called departments with, in this case, also 3 columns: the department ID, the department name, and the budget. Each of these will be, the underlying thing here will be called the primary key. The key, again, is the thing of which you will be creating an additional file, the index file, which is the data structure, such that you can easily, quickly, efficiently navigate to the rows that you care about. So, maybe if I have, these rows, I care about 2 social security numbers. How do I find this row to return and this row to return quickly? That will be using, I don't know, maybe a hash table for the social security number. So in order to return these rows, we'll have a hash. Wait, isn't that writing? Some hash function where f of s of the social security number will return some number. Okay, and so you'll have this separate hash table, which will correspond to the social security number, and that's it. You give it a social security number, it will give you a number. That number will correspond to a particular row, and this is the whole reason why we had the background in foundations talking about these things. All right. The specifics of the table, this part, all the actual data itself in employees, this is not captured in the ER diagram. Same thing here. This data is not captured in the ER diagram. The ER diagram is a more high-level view of the structure and the relationships that this data has. So as far as the things that matter for ER diagrams, it's going to be the name of these tables and their attributes. And so we see those here, and we see these here. We'll get to the, I know I'm not covering this yet. We will get to that. That will also be a table, just to let you know ahead of time. So these diagrams are, again, meant to capture, at the end of the day, how to create tables. Tables are also called relations. So that's a relation. This is a relation. That is where relational databases comes from. It's that you can think about everything in terms of just tables. And also this is where, not this class or the next class, but very soon when we talk about relational algebra. The relational part of that comes from this. These are relations. So this stuff here, this is sort of a preview of where we are going. So I'm just giving you a preview for that. Okay. Actually, I'll keep this here. That's a relation. This is a relation. A relation is just a table. All right. Now, let's talk a little bit about these constraints, the participation constraints. Here, we have, again, these participation constraints only refer to the connections between the entity and the relationship. These thin lines mean that it's unconstrained. These are. So what that means is that an employee has a relationship to a department. Because that relationship is unconstrained, it means that an employee can work in no department, it can work in exactly one department, or it could work in many departments. Okay? They're unconstrained. These are the only three possibilities: 0, 1, more than 1. So three possibilities. In an unconstrained relationship, any of those are okay. Similarly for departments. And now with each of these entities, you have to go from the way that A is connected to B, but also the way that B is connected to A. So in this case, an employee can work in no department, an employee can work in exactly one department, or an employee can work in more than one department. Going the other way, a department can have no employees, a department could have exactly one employee, or a department could have many employees. With the way that our diagram is drawn, all of those, any combination of those is fair game. Oh. If I do this, a thick line, what this says is that an employee can work in 0 departments, could work in exactly one department, can work in many departments. The employee is unconstrained in its relationship with the department. But the department now, this is a thick line. And so what that says is that every department has at least one employee. Like a department devoid of any employees is something that we won't recognize because there's a thick line. Okay, so departments cannot be empty. If I do this, that's a thin arrow. Now, departments can have departments have to have at least one employee. Employees can work in at most one department. So an employee can work in 0 departments. This diagram allows for that. But an employee cannot work in 2 different departments. That is not allowed, according to this diagram. Okay, so let me pause because I've been doing a whole bunch of talking for this class, and I like to hear from students as well. So, um, how do you feel about ER diagrams so far? Are you following? Do you have questions? Are you lost? It's a good review from MIS. Yeah, so um, I think that some of you, maybe not all of you, have some experience from this from MIS. That being said, this course I'm teaching completely self-contained, so if you have no experience at all previously with this, we're covering everything. Also, in the previous section, I had a student after class say that after MIS that there were certain things that she was never quite comfortable about in her previous teachings for MIS. And if that's you, somebody in this class, like there's some place where you got stuck in the past or you weren't quite clear on it, email me or send me a message on Canvas or something, because if we can cover any of the gaps that might have previously been left over, I'd like to do that. I'm not going to be spending a long time at all on ER diagrams. Like I said, it's going to be 2 classes, maybe less than that. I mean, potentially by our next class, we'll be already moving on to relational algebra. But okay, so let me pick on, I don't know. I'm flipping a coin here. I'm just rotating. How about Hassan?
Hello.
Hello. Okay, so you're following for ER diagram so far?
Yeah, kind of.
Kind of. Okay. So before I change the ER diagram that we have on the screen, I'll repeat. Um, Basically, most of this is relying on the participation constraints. That's the really important part for this lecture. So this left arrow that's circled in green, that says that an employee can work in at most 1 department. So an employee can work in 0 departments. I'm sorry, an employee can work in 1 department, yeah, or 0 departments. Both of those are okay, but an employee cannot work in more than 1 department. An employee can work in 0 departments, and it can work in 1 department because it's got this arrow. So an employee can work in at most 1 department. This here on the right corresponds to this, and that says that a department has at least 1 employee. So a department can have 1 employee, a department can have many employees. Both of these are okay. So this is what I would call phrasing things in English. All right. Okay with that?
Yeah, it makes sense. I got it.
So now I'm going to delete these, and I just basically want you to state in English what this means. That's a thick arrow. That's a thin line. So how would you state? How would you make a statement about employees, and how would you make a statement about departments in plain English, given this diagram?
I'd say employees um working at least one employee works in 0, 1, or many departments.
Hold on. An employee, at least 1 employee works in not quite right. Why do you say at least one employee?
Because it's a thick line.
So this is not only a thick line, this is a thick arrow.
Okay.
So an employee can work in exactly one department. So there's no employees that work in 0 departments, and there's also no employees that can work in many departments. Every single employee works in exactly one department. Okay?
Got it.
Got it. Okay. So say it back to me then. This one.
So the employees work in at least one department.
At least one?
Could be more.
It cannot be more.
Yeah.
It's exactly one.
Yeah, exactly one.
Exactly one. Right. So you can't have an employee working in more than one department. The thick arrow is a combination of, because of the arrow, at most one, and because of the thick line, at least one. These combined, it means exactly one.
Oh, okay.
Employees work in exactly one department. No more, no less. Exactly one.
Okay.
Okay?
So they work in exactly one department.
Yes, perfect. Good.
Okay.
All right, how about now, how about the departments?
So the employees work in exactly one department, and then the department can have so it's relationship between the department and employees, right?
Yeah.
So the department can have at least one employee.
That's not a false statement, but it's not a complete statement.
Can they have none employees?
They can. Mm-hmm.
And they can have multiple.
And that's also true. And that's now it's complete. Yep.
Yep.
So they can have 0 employees, they can have 1 employee, they can have many employees.
Yep.
Very good. All right. Thank you very much.
Yep.
Let me pick on, how about Karnik?
Can you hear me?
Yeah, very well. Same thing, just state in basically plain English. You do this. Yeah.
Okay, so at least one employee can work for at least one department, or at most one employee can work with at most one department.
Okay. A suggestion: don't make these 2 arrows into one sentence. Make each arrow its own one sentence. So I'm going to say a sentence about employees, and then separately from that, I'm going to make a sentence about departments. I think that will make things easier. So for the sentence for employees, what is your sentence for that?
So we can say, for every department, at most one employee can work.
For every department, at most one employee can work. Okay, so you're describing this one. Yeah.
Oh, okay.
Mm-hmm.
So for every department, at most one employee can work. Is that the one you circled?
For the one that I circled, I would say that, yeah, every department has at most one employee.
Okay, so for the other one, we can say at most one employee can work in each department.
I would say start with the employee. Any employee can work in at most one department. So for this arrow, yeah, you kind of start with the entity. Then, so you talk about the entity, then the relationship, and then the thing that it goes through. So for this green arrow, the words appear in that order. So one employee will work in at most one department.
Is that the case for like all the relationships? So if we were to describe the other arrow, would we start with department first to explain it?
Very good. Yep. So if you're doing it this way, then you start here for any department, and now this would be 2, and then this would be 3. Yeah. How about can you state this one? Mm-hmm.
Yeah. So every department can have at most one employee.
Perfect. Nailed it.
Okay.
Very good.
And so the other one will be every employee can work in at most one department.
Perfect. Yep. Exactly.
Okay.
Yep. Every employee can work in at most one department. Yep. Very good.
Okay.
Yeah. Excellent. Yeah. So each of these arrows deserve their own sentence. Because there's 2 arrows and 2 entities, you're going to describe it in 2 sentences. The first sentence, focusing on what I've circled in green, every employee works in at most one department. That's the first sentence. The second sentence here is every department can have at most one employee. And that's the way to state it in English. Or, if somebody gives you English, then you can translate that English into this diagram. And that's really the way that it would go. You're going to be talking with somebody who, you can talk to them about, okay, you have data on employees and data on departments. Can an employee work in more than one department? Can a department have more than one employee? Are there some departments with no employees? And you ask a series of questions, you get answers to them, and then you can generate this diagram. So we're kind of going backwards. We're starting with a diagram, and I'm asking how to phrase it in English. In the real world, you'll be given English, and you should translate that into a diagram. So, fine. Okay. So that's kind of it for ER diagrams. Yeah, there's really not a whole lot more to say about constructing an ER diagram. There's a lot more to say about this part, translating an ER diagram into tables. And this is what I can touch on a little bit today, and we'll finish the next class. I'd like to give at least one example of this today before the end of class. But just to make sure that we're comfortable on the ER diagram part of it, I'm going to pick out another student and ask to say in English how to describe this ER diagram. So how about Nick? Nick.
Hello?
There we are. Hello. Yes, I can hear you very well. Okay. Let me do, I don't know, I'm just making stuff up. How about this?
Those are both thick ones, right?
So the one on the right is a thick line. The one on the left is a thick arrow.
All right. So every employee would work in exactly one department, and every department has at least one employee.
Perfect. That's it.
Yeah.
Okay. Yeah.
All right.
Very good. Thank you.
Thank you.
All right. I think that's enough. If you're still uncomfortable with it, feel free to draw a diagram. Draw different diagrams. Draw different arrows and stuff, and write things down with how you'd phrase it in English. You can take a picture and send it to me, or if you're not quite sure, you can draw a picture, send it to me, and ask how would you phrase it, and I'll respond. But so far, I'm comfortable that I think most people get it. So, yeah, let me move on. Let me stop this video because I want to do some more writing. By the way, if you have questions now, just throw them out. You can unmute yourself. You can type it in the chat. Any of those. All right. So I'm going to use this as sort of a running example. If I can actually highlight it. Okay, there. Is that highlighted? Come on. Stupid. Highlight. Got it. Okay. So when we talk about ER diagrams, it's just these diagrams, okay? These tables are kind of how these diagrams will be applied. I think we're done with the diagrams. I think we've talked about everything that there is about it. So now I'm going to focus on this translation. How to go from a diagram to build your relations. Next. Stupid copy. What is so dumb? Okay. So we're going to be talking about these different flavors. Let me separate these a bit more. So the easiest one is when things are unconstrained. Which are thin lines. Okay? There's not going to be any changes here. So the employees, again, each of these entities, the entities are the easy part. Okay? For each entity, for sure, every entity is going to be translated into its own table. Okay, so here we have the employee entity, that gets its own table, and then here we have an entity that gets its own table. That's the easy part, right? The name of the entity is the name of the table. The columns of the table are each of the attributes for that entity. And at least one of these entities is going to be keyed, which is the underline. Again, the key is the thing that will be the data structure. A B plus tree, maybe a hash-based index, whatever. But for this table, there's going to be at least one attribute that will have an index file. for efficiently returning rows of this table. Okay, I'm not going to go into detail about how to construct that data structure because that was the whole point of the first part of the course. Okay, so the question here is, what is this? How do we capture the relationship? So here, we have data on employees. We have data on departments. Now, there's a relationship between employees and departments. How do we capture this relationship using tables or using relations? Here, this can be captured with another table. And this table is going to be called works in. And the point of this table is to connect these two together. All right, so we'll have three tables. One table employees that's just about employees. Another table departments that's just about departments. And now we have a third table whose primary job is to connect the employees table and the departments table. So first, this relationship has an attribute. So we know that we'll have at least a column for that. But because this relationship is connecting to employees, and employees has this primary key, so will the works in table. Similarly, the works in also connects to departments, and departments is going to be defined with its department ID. So it will have that as an attribute as well. Okay, so the works in table, it's doing this connection between these two tables because this table, employees, has a social security number as a primary key, and that is going to be captured here in the works in table. And the department table is keyed by the department ID, so that is, now this department ID is also going to be showing up in this table. And because both of these keys, one from the employees table, one from the departments table, both appear in the works in table, that is going to define the connection between these, the employees table and the departments table. And then we have, the since, just because that also appears as an attribute of this relationship. Okay. Now, that is also fairly straightforward, I hope. But tables have to have keys. Okay? Again, for when you're going through the background, each table, think of it as a gigantic table, like a massive table, millions of employees and hundreds of thousands of departments. I mean, imagine every table as being massive. So each table will need its own data structure, its own index file to be able to efficiently navigate through it. And that index file is built based on a particular key of that table. So the departments table is going to be unstructured on a hard disk, So the employee or the departments table might be on one hard disk, all of the departments' data. But then you're going to have a separate index file based on the department ID. Maybe that's a B plus tree. And so that way you can efficiently navigate to whichever department you want. Give me a department ID, and I will very quickly return to you all of the entries associated with that department. So similarly, the employee, the employees table, imagine it being gigantic, is going to be somewhere on hard disk. If you give me a social security number, then I can return to you very quickly any particular employee. So that's why we have that keyed attribute. Now, the works in table, also imagine it is being gigantic. It's also on disk. And so we want to be able to efficiently return one or more entries in the works in table. To efficiently do that, we have to have a data structure that will be captured as a small index file. But we need to know how to create that data structure. What are the keys for this data structure? Let me turn this off now. Okay, what are the keys here? First of all, let me ask anybody. I mean, I guess maybe some of you have seen this before in your in MIS. So for this ER diagram, when everything is unconstrained, what would the keys be for works in? A combination of SSN and DID. The primary key is the combination of SSN and DID, I think. Very good. Yes. So here, the key is going to be both of these. This little double arrow thing here, that is called a combination key. Oh, why is the name escaping me? Not convex. Oh, geez.
Composite key?
Composite key. Thank you so much. Oh, it was on the tip of my tongue. All right. Yeah, that is a composite key. Okay. Thank you so much. Oh, I was great. You guys are typing it. I had my eyes shut, trying to rack my brain for it. Okay. Thank you guys. Yes, very good. So, a composite key is when you take two different values and you glue them together. All right. So let's first of all, just to reiterate, or actually, I don't think I've said this yet. From here on out, keys are going to be unique. No repeats. Okay, if you try to repeat a key, you're going to have a problem, an error. So if we look here at the employees table, for example, if I tried to add, why isn't it written here? If I were to try to add this entry here, Amy, I would get an error because these keys, or that that 4444, that key already appears. So I will not be able to add this entry. Okay, I'd get an error because the keys have to be unique. Okay? Right, so that's why that's an error. Similarly here, if I wanted to add a department, I don't know, even if I wanted to add the same department, error for the same reason, right? The key appears twice, or the entry appears twice on a keyed attribute here. So that's not cool. That won't work. You will get an error. So for the composite key, let's say that John works in accounting since 2012. If I wanted to have John work in accounting in 2013, that is an error because the glued together keys appear twice. However, I could have John working in, that one's fine. This one's no good. But I could have John working in, he started off in accounting, and at some other point, I don't know, he's now playing a dual role. He's working in two departments. John, 1111, is working in both Department 1, accounting, and Department 2, HR. There's no conflict here. Even though this appears twice, no problem. This social security number can repeat itself, unlike this social security number, because in the employee table, that social security number is the only key. But here, in the works in table, although the social security number appears twice, the combination of the social security number and the department ID are different. So each of these entries are okay. All right. And this is reflective of the fact that here, it's an unconstrained relationship. Okay? So already, we have one employee, John. He works in two departments. He works in more than one department. And that's okay. That's okay. Because it's unconstrained. All right, so that would be a valid entry in the table for this unconstrained relationship. You could have an employee, oddly enough, working in no department. Let me throw Paul in a department. Paul 2. He's also in HR. He's a new guy. So again, here the department ID repeats itself. While in the department table that is a problem, here it's okay. In the department column, you can have repeats so long the social security numbers differ. Okay, so that's what a composite key is. Okay, it's the combination of two different or two or more values. They're glued together. And it's that glued together thing that has to be unique, which is why this entry is no good. Because the combination here and here are identical. So that would be an error. But if you just change one of them, then it's good, as is the case for this third entry and this fourth entry. And in the third entry, the social security number repeats itself, no problem. In the fourth entry, although the department ID repeats itself, it's okay because the social security numbers differ. So that's also a valid entry. All right. Now let's look at this table and the values in the table and compare it to the ER diagram. Here, I'll just re-highlight it for fun. Here, that means it's unconstrained. An employee can work in no department. All right, there's Paul. He does not appear here. Paul doesn't work in any department. That's okay, because it's unconstrained. So these tables are valid. Can an employee work in one department? Sure. There you go. Peter. Peter, he works in one department. So the tables are still valid. Can an employee work in more than one department? Sure. There, look at John. Here. John works in 2 departments. Right? An employee can work in 2 departments. We see that in the table. No problem. These tables are still valid with respect to the ER diagram. Okay. Let's look at the departments. This one. Can there be a department with 0 employees? Yes, this is unconstrained. For example, the IT department is empty. There's no employees. This does not appear in the works in table. No problem. It doesn't have to, because it's unconstrained. You can have empty departments. So we're good. You can have a department with exactly 1 employee. In fact, right now, the HR department has exactly 1 employee. No problem. The tables are valid. Can you have a department with more than 1 employee? Yep, it's unconstrained. In fact, here, the accounting department has 2 employees. Everything's valid. Okay? So this is, I think, one of the easiest cases. When you have entities, I can't see myself. Hopefully I'm kind of in frame. When you have entities that are unconstrained, this is kind of the easiest case. Again, the entities are quick work. All right. Each entity, the entity itself is going to be the name of a table. Each of the attributes are going to be columns for that table, and you start there. Okay, so for each entity, it's going to have its own table. Done. The hairy part comes in dealing with the relationship. In the case that it's an unconstrained relationship, then that relationship can be represented in its own table. And for each entity that connects to that relationship, the primary key will appear in that relationship table, and each of those keys will be combined together in a composite key, just like this. Okay, so that's it. The next class, we're going to do the same thing, and you could even practice with it if you want. Try to take this same diagram and then add, I don't know, a thick line. And then can you come up with the tables and the keys such that such that a department has at least one employee? What would that make the tables look like? Or if it has at most one employee, what are the tables? What are the keys? Or some combination of them. This kind of thing. All right, so that's the whole point of ER diagrams, is it's to try to figure out how many tables you need and what are the keys in order to align with those constraints. All right, so that's it. Thank you guys. I'll have a good weekend. I'll stick around if you guys have any questions.